We're going to talk about sequences and series and summation notation. Now, sequences are a set of numbers. It's an infinite list of numbers that have some sort of relationship. We usually call each element in the series by its position in the series. The first term we'll call a sub 1, the second term a sub 2, and you can see it just keeps going and going and going. And according to the place that it is in the series and this little subscript number, we can determine an nth term or a formula that if we start in at 1 and we iterate through all of the integers starting at 1 and going bigger and bigger and bigger, if we put that into our formula, for instance, if the formula is a sub n, where it equals, the formula is 5 times n, well, when n equals 1, 5 times 1 is 5. When n equals 2, 5 times 2 is 10, and so forth. So a sequence is just a list of numbers with commas in between them, but there is some formula that will generate that list or that sequence. And then we'll see that every sequence has its series that goes along with it, and we'll talk about series in just a little bit. But in particular, sequences are a list of ordered numbers that have some sort of relationship. We talk about the first term, and the first term in a sequence is a very important term because that term in the formula where n equals 1 determines all the rest of the numbers in the sequence. The nth term is also very important because the nth term is what we use to define the formula. So if they'll give us the nth term or we can determine the nth term, we could generate every single number in that sequence just from the nth term alone. So here we're going to attempt to find the first 5 terms and the 100th term for all of these sequences. Let's look at A. A sub n, the nth term of this sequence, is 2 times n minus 1. And remember, unless we're told otherwise, we always start at n equal 1. So we could generate the first term in this sequence as 2 times 1, which is 2, minus 1. So the very first term in this sequence should be 1. The second term, a sub 2, is going to be 2 times 2, or 4 minus 1. So the second term would be 3, and so on. We'll continue going through that until we generate those first 5 terms. Here's a sub 1, a sub 2, a sub 3, and so on. Now, if we want to generate the 100th term, or the 3,000th term, or the 1,000,001st term, all of that is based on n, because the 100th term is a sub 100, so we would just plug 100 in here. That would be 2 times 100, or 200, minus 1. That's where we get 199. And you can see n squared minus 1, where n equals 1. 1 squared is 1 minus 1, so the first term is 0. If n equals 2, which is the next integer value that we're going to plug into these sequences, 2 times 2 is 4, 4 minus 1 is 3. Fractions are a little bit more tricky. You have to look at the sequence that is the numerators and come up with an nth term for that, and then separately look for the term that is, or the sequence that is in the denominators, and try to come up with an nth term for that, and then show those as a ratio. So here on C, n over n plus 1, where n is 1, we get 1 over 1 plus 1, or 1/2. Where n is 2, we get 2 over 2 plus 1, or 2/3. So you can see how that would generate that sequence. For the 100th term, we would get 100 over 100 plus 1, and that's where we get 100 over 101. Now, when we look at the signs, the positive and negative signs to each term in our sequence, we have to take into account whether they're all negative or whether every other one of them is negative. And if every other one of them is negative, we're going to need to remember that we're going to take negative 1 and we are going to raise that to the power of n. Because when n starts at 1, we would have negative 1 to the 1 power, so our first term would be negative. Then when n equals 2, we would have negative 1 squared. That's what's going to give us our positive term. When n equals 3, we would have negative 1 cubed. That would make the third term negative. Now, we have to pay attention to this too. We would change this a little bit if our first term was positive, but our second term was negative. So that might look like -1 to the n plus 1. So we'll practice those ideas, but not every term in your sequence is going to be a positive term. And if they alternate, then this kind of idea is going to help us alternate those signs. And we can see in the bottom that it's just 2 to the 1 power, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, and therefore the 100th term would be 1 over 2 to the 100th. So that kind of idea, it's not very difficult to go in that direction. If you give me the formula, if you give me the nth term, it's very easy for me to generate all of the terms or any particular term that you ask me for. What's a little more tricky is if you give me the first 4 or 5 terms in the sequence and you ask me to find that nth term. That takes practice. Don't get frustrated with it. You'll begin to see that there are ways that, oh yeah, I remember if it was every odd number, or I remember if it was every even number, it could look like this. Again, we're going to remember what we need to do when we have to alternate those signs. So this does take practice, and don't get frustrated with the process of it. So let's look at how we might find the nth term for the sequence in part A here. First, like I said, we're going to look at the sequence that is the numerators, and we can see that all the numerators are odd numbers. We're going to start with 1. So we need when n is 1, we want it to generate 1. When n is 2, we want it to generate 3. When n is 3, we want it to generate 5, and so forth. So the odd numbers are of the form 2n minus 1. So when n is 1, we'd have 2 times 1, which is 2, minus 1. Sure enough, that gives us the 1 here in the numerator. The next n has got to be 2, so 2 times 2 is 4, minus 1 is 3. Sure enough, let's try it for the third term. When n is 3, 2 times 3 is 6, minus 1 is 5. So remember that. If you are just generating, or your sequence numerator or denominator involves odd numbers, that looks like 2n minus 1. When it's the even numbers, that's pretty easy. When n is 1, I want 2. When n is 2, I want 4. When n is 3, I want 6. So that's just going to be 2n. So we're going to have the ratio of 2n minus 1 over 2n, and that's going to be our nth term for that sequence that's in part A. Now, the sequence in part B, which is just powers of 2, 2 to the 1, 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th. So the actual nth term is easy to find, but we have to remember that we are alternating those negative values and that the first one is negative. So that -1 to the n power is going to come into play. And so they're powers of 2 and they alternate in sign. So we know we have to have 2 to the n, but we also have to have that alternating term in there. And we're going to use -1 to the n because that first term is negative. So like I said, it just takes practice. Now if I have a sequence of numbers, a sub 1, 2, 3, 4, and so on, up to a sub n, and I add them together. That's the difference between a sequence and a series. A series is nothing more than the sum of some sequence that you're working on. So if I have a sequence of numbers with the commas in between them, I drop the commas and I put plus signs. That is a series. A series is a sum of a sequence. The notation is a little bit different if you haven't seen it before. It's called summation notation. This is a Greek letter for S. It's called a sigma. It's always also sometimes why it's called sigma notation. So if we are dealing with a series and they want us to find the sum of the series, or write the sum of a series, then the sigma notation has different parts to it that have different meanings. We write something on the bottom of sigma, something to the right of sigma, and something on top of sigma, and they all have a meaning that we have to pay close attention to. But as soon as we see sigma, we know that we are going to add every term that is in the sequence that is given to us as a sub k. And so let's look at what all the parts of the sigma notation mean to us. So the k equal 1 on the bottom tells us where to start with k. Now, k and n mean the same thing here. We can't say we're going to start at n equals 1 and stop at n. That's why they've brought k. They also use other lowercase letters from kind of the middle of the alphabet. You might see a sub I, you might see a sub L or a sub J, a sub K, a sub N. All of that means the same thing. This is a sequence. This tells us where we start. We're going to start adding at the first term, a sub 1. We're going to stop adding at the nth term, a sub n. So this tells us to add, the sigma notation tells us to add, and this tells us where to stop, which term to stop in our sum. So let's do some practice. Here in A, we have the sum of the sequence k squared. We're going to start adding when k is 1, and we're going to end at the 5th term, 5 squared. So let's see what that would look like. The first term, when k is 1 squared. When k is 2, we'll have 2 squared. When k is 3, we'll have 3 squared. When k is 4, we'll have 4 squared. And when k is 5, we'll have 5 squared. So we started at 1, we iterated through the positive integers, and we stopped up here at n where they told us to stop. So we would get our calculator out, we would add all of those integers, and so the sum of the first 5 terms of the sequence that is defined by k squared is 55. Now let's look at B. B says to start at j equal 3. We are adding the terms in the sequence that's 1 over j, and we're going to stop when j equals 5. So we should expect to see 1/3 plus 1/4 plus 1/5, and sure enough we do. We find a common denominator, we add those together, we get 47/60. Now on C, here's where they're using I. It means the same thing as k, the same thing as n. So we start at I equals 5, and we stop at I equals 10, and I is just I. If my first term is the number that I start with, then that's my term. So we're going to start with I equal 5, and we are adding I. That's what this means. Here we're adding 1 over j where we start with j equal 3. Here we're adding I where we start with I equal 5. So it literally is 5 through 10 added together. So that sum is 45. On D, we don't have a letter in our sequence. This says that every term in our sequence from 1 to n is 2. So this is just adding 2 to itself how many ever times it tells me to. So I'm going to do that starting at 1 and stopping at 6. So I have 2 added together 6 times, and that's 12. So these sums are very easy to work with. There are a couple or a few properties of sums that I want us to know. If we're adding sequences, it is true that if we have 2 terms that are added together, 2 sequences, nth terms or kth terms added together, that I can add up the sum of the first sequence and add up the sum of the second sequence and add those together, and I'm still going to get the sum of the sequence that said it had 2 terms. In other words, series break up over addition. It's also true that series break up over subtraction. I have to make sure that I subtract these in the right order, however. Here on the third property, C is a constant. 2, 3, -1, 10, 1,000, whatever it is. It's just a real number. It could be 1/5, 1/3, -1 over pi. It's some constant that is included in every single term of my sequence A sub k. Well, what I can do, instead of carrying C along in every single term that I'm adding together in this series, I can just factor that constant out front, which is what they've done here. Find the actual sum of the sequence, or find the series sum that they've asked for, and then multiply that result by that constant. And that's going to get me the same result. So there are sequences and series, summation notation. Come to class next time and we'll do some practice problems.